Okay. Let's go ahead and get started. So today we're going to start talking about weak bases. So we've talked about weak acids yesterday, where we saw the equilibrium expression Ka referred to the acid dissociation. We're going to see we have another one called Kb, which is for base dissociation. The base dissociation formula will look something like this. I'm just going to use the conjugate base A minus in this particular example, but it could be neutral species, doesn't really matter. We're going to see that it will combine with water. So we'll have some aqueous component there combining with water to make HA plus OH minus. Both of these would be aqueous. So whatever A happens to be, it could be, again, something neutral. It could be charged. Doesn't really matter. But if we take a look at the equilibrium expression for this, we're going to see that it's going to be equal to your protonated species, your hydroxide, and then your deprotonated form. As always, we will omit pure liquids, so just like before, we don't have to worry about the water because that's a pure liquid. Technically, that's part of our Ka as well, but we kind of just use H plus instead of H3O plus. So if we were to just kind of put this in context, let's say we had some ammonia that was aqueous. We could see that the equilibrium that would form would make the ammonium and hydroxide ions. And so Kb for ammonia would be equal to NH4 plus. That's the protonated form. Little one, what are you doing down there? You want to come up here? Okay. Hi. This is one of the new ones, by the way. This is Miss Jersey. Is that so? Okay. So in this case, our A minus would be ammonia and our HA would be ammonium. Again, here the difference is a positive charge, one more positive charge, and then one more hydrogen, which is the H plus, of course. And we're going to see that this equilibrium is going to work exactly the same as it did for acids. So if we go ahead and look up the Kb for ammonia, we can go ahead and do some work with it. Let's see. Let's go to Wikipedia here. Look up ammonia. So your homework, I did just say you can use Wikipedia for these things. Let me show you where to find some of these values. Is this? Okay, hold on. Let me... New window, I suppose. Yeah, that works. Okay. With these, if you just look up a particular compound, you'll see, if you just kind of scroll down to some of these properties here, you're going to see various factors. Here, we're going to be looking at acidity and basicity here. As you can see here, the pKa for this is huge. 32, that's 10 to the minus 32 would be its Ka. It's not likely to lose a proton. But its pKb is 4.75. So let's go ahead and write that down. 4.75. And we're going to work with this in just a little bit. So we'll be able to calculate the pH of a solution of this. We're going to see it'll be the same thing. What shall we say? What compound do we want to look up? I don't know, sulfurous acid. We're going to see that, again, it's going to give us our acidity values as pKa's. Notice this is a diprotic acid. We're going to have two pKa's here, pKa1, the lower one, pKa2, the higher one. Remember, lower pKa is more acidic, so you'll be using similar things to on your homework. Okay, I'm gonna put you on the couch. I know you want to be picked up, but you're gonna bite me, so I'm going to ignore you. All right. Anyways, so here is our pKb for this. So let's go ahead and figure out what is the pH of, I don't know, how about we do 6 molar ammonia. Pretty concentrated, but let's go ahead and see what this is going to be. So, just like before, we're going to want to construct an ice table. And if I were smart, I would have just copy-pasted the whole thing, but oh well. We're going to start with 6 molar here. The water doesn't really matter again because that's not part of our equilibrium expression. We don't have to include it in there. We're going to start with nothing for our other ones. Of course, as a result, we'll be subtracting here. And notice it's exactly the same as before. Let's go ahead and solve our Kb, by the way. It was 4.75 is pKb. So we can go ahead and do that. 10 to the negative 4.75. Oh. 10 to the... Oh, goodness, I'm not deleting enough. Okay, that's the problem. All right, so that value is 1.78, we'll say, times 10 to the minus 5 molar. And so just like before, we can go ahead and we can try our assumption. Let's see if we can just make x not exist. So we'll multiply this number by 6 and do a square root. If we do that, we get x is 0.0103. Let's double check. Actually, we can see right away this is definitely less than 5%. 1 over 6. I mean, 5% would be 0.05 over 1, so we don't, we're okay here. So we can use our assumption. And so that's going to be our OH concentration here. With that in mind, we can figure out what the pH is, right? We can solve for the pOH and then subtract 14. Or we can use the KW expression to solve for the what am I trying to say? Concentration of hydrogen directly. But since we're just asking for pH, this way is, I think, a little bit easier. So let's do the negative log of the answer here. Negative log answer. Oh dear. Go away. Okay, there we go. Negative log of the answer. Okay, is going to be 1.9859, whatever, 3 sig figs. And for pH, remember pH plus pOH is 14. And so the pH is going to be 14 minus 1.9859. Which Kevin says is 12.014, which looks fine to me, with 3 sig figs, which is nice. And that would be our final answer for that. So that would be our answer for this particular problem. Cool. So really just the same thing as yesterday, except one more step of going from pOH to pH. Hooray. If you wanted to do percent ionization, we could do the same thing like before. For the base, it would just be, instead of having the, instead of having the H plus, we would just use the OH minus at equilibrium. versus our A minus at initial, whatever that happens to be. And so that would be the 0.0103 over 6, which would be, if we really wanted to find this out, except I forgot to put numlock on, 0.0103 divided by 6. That's going to be 0.17%. So very small percent ionized here. So, but we can do exactly the same things with bases as we can with acids. We just use a different constant. Alrighty, any questions on that? Where's my tea here? Alrighty. Then let's kind of take a look at a few things here. So, for the ammonia, its pKb was 4.75. If I were to tell you, let's go to Wikipedia again, and let's find ammonium. We'll see its pKa is 9.25. Perhaps we'll notice something about these two. Perhaps we'll notice that those two added together is 14. Just like pH and pOH. Curious, isn't it? So the pKa plus the pKb for an acid and its conjugate base, or a base and its conjugate acid, either way, will equal 14. So notice here we have our base and its conjugate acid. We add their pKa and pKb values together, and we get 14. And so we can see the same relationship is going to be where if we had OH and H+, it's the same relationship, right? So we're going to see that the Ka, doesn't need brackets, sorry, and Kb for a pair of conjugates, yeah, it'll be at 4. Yeah, typically these are going to be at a given temperature, right? Because an equilibrium constant is always dependent on temperature. With that being said, these might be constant. I haven't thought about that. No, actually, I think this probably is more going to be constant than having a temperature dependence. Just because they would be reverse processes, right? Reverse reactions. So if you were to, so one of them would be endothermic, one would be exothermic. If you're increasing the temperature of one, you're going to increase its K, and then the opposite one, you decrease its K. So presumably the relationship should still hold. So I'm going to go and ahead and say it's probably not strongly temperature dependent, but I'll look that up just in case. But suffice it to say, this one is definitely temperature dependent because Kw is temperature dependent. But the Ka and Kb for an acid will equal Kw if you multiply them together for an acid and its conjugate base, or for the reverse of that. So with these, we can figure out a lot of interesting things here. So we know that HF, for example, is a weak acid. And we know, therefore, the conjugate base of that acid is the fluoride ion. And we would expect it, therefore, to be a weak base. If we go ahead and look up the pKa of hydrochloric acid, here it is. Its pKa is 3.17. we would expect, therefore, the pKb of this guy would therefore equal, let's see, 10.83. Just by using this math, so 14 minus 3.17. Let's go ahead and double check. Let's take fluoride and put it in Wikipedia and see what we get. Apparently it doesn't have a pKb value given here. Oh well. Hopefully all the ones on the homework will have them. That's a pity. This one doesn't seem to have it. Oh wait, here it is, here it is. It's not written on the table though for some reason. It is written down here as 10.8. Alright, so we can see by comparing these two, just like a pH of less than 7 was acidic, a pKa of less than 7 will be acidic as well. So if we're comparing an acid and a conjugate base, we can take a look at the pKa of the acid to see if it will be acidic in solution or basic in solution. If we take a look at our what was it? What did we do yesterday? Bicarbonate or something? If we look at the bicarbonate ion, yeah, I think we looked at bicarbonate. Let's go ahead and get its values here. Bicarbonate. Notice that bicarbonate is amphoteric, right? Or amphiprotic, whichever way you like to describe it. It could act as an acid or a base, right? It could turn into carbonic acid or it could turn into carbonate. The pKa of this is going to be, where is it? 10.3. The pKb of this is 7.7. Notice that these don't add up to 14 because it's obviously not its own conjugate base or acid, right? Hopefully that part is obvious. This pKa is between bicarbonate and carbonate, and this pKb is between carbonate and carbonic acid. That would be the conjugate pairs we're looking at here. If we're looking at bicarbonate, just looking at it here, do we expect bicarbonate to be more likely to act as an acid or as a base? Let's write that down. Yeah, right. So it's definitely going to be more likely to act as a base. We can see that because its pKb value is lower. So it's going to be a base as a result. So the for something that's amphoteric, if Ka is greater than Kb, it's going to be acidic, or more likely to be an acid. If Kb is greater than Ka, it's going to be basic. Notice the logarithm ones of those are the opposite. So that would be the same as pKa is less than pKb, or pKb is less than pKa. Remember, that's inverted. So you can compare either one, either the logarithm value or the actual equilibrium constant here. So we can predict what something is going to behave as. All right. Let's take another example. Let's look at this particular ion here. Dihydrogen phosphate. Actually, let's look up phosphate and let's do it this way instead. Let's look up, or phosphoric acid, my goodness. Phosphoric acid. Okay, let's look up its pKa's. So, where are our pKa's here? Acidity, where are you hiding? Density, melting point, solubility. Ah, okay. So it's pKa's. If we look at phosphoric acid, sometimes you're going to have to search the page, or you can just Google them. Honestly, you'll probably get a lot of your pKa's out easily that way. 2.14, 7.20, 12.37. These are the pKa's for phosphoric acid. So let's go ahead and evaluate this particular one. Let's see how it would react as an acid and how it would react as a base. So if it's going to react as an acid, let's just do that one first. We're going to expect it to kick off its proton and form that. Which equilibrium does this correspond to? Which of the pKa's are going to be appropriate here? Hi, little Jersey. You should be looking at pKa2, right? Because it's the second dissociation. Not quite. pKa3 would be removing the third hydrogen. So in this case, we're removing the second hydrogen from phosphoric acid. All right, if we're looking at its ability to react as a base, we're looking at this equilibrium. And so which pKa is this one going to correspond with? Or rather, well, we'll see. Well, this one should correspond with the pKb of pKa1. So this one is a base dissociation, so we're looking at this one is actually going to be pKb1 because Ka1 refers to this particular acid, and so it's going to be the inverse process of that. So so technically this will be the pKb associated with pKa1. So remember that this is going to be the conjugate base of phosphoric acid. And so phosphoric acid's acid dissociation, which is pKa1, is going to be related here. So it's going to be the opposite process. We would see that for this one and then this one, this is where we would have those other ones. That's where those two would come in. It's because we're looking at the conjugates here. All right, so I know lots of letters and numbers here can get confusing. So this one is the reverse reaction, the base reaction of pKa1. So if we're looking at that, we're going to have a pKa of 7.20. And if we're going to calculate the pKb of this one, we're going to see 2.14, which is going to be, what is that going to be? I know how to do math. 11.86, maybe? That seems reasonable. So if we're comparing these two then, what do we think is going to be the winner here? Is this substance more likely to act as an acid or a base? Hopefully we should see that this is more likely to act as a... it's an acid. Acid. We're comparing the pKa and pKb values, right? So 11.86 versus 7.2. I'm glad we finally got something that's slightly confusing. So let's go ahead and look at it again. So if the pKa is 7.2, the pKb is 11.86 for this particular ion. Remember, for pKa, we choose the lower one. So because pKa is less than pKb, this will be acidic, or it will be more likely to act as an acid. Let me just write that out instead. More likely as an acid than to react as a base. If we were to find the Kas of these and Kbs, you would see that if we were to calculate that Ka would be greater than Kb for this one, if you wanted to calculate them. I mean, and we can do that, right? I mean, Ka would be 10 to the negative 7.2, and Kb would be that. We can see definitely 10 to the negative 7 is definitely greater than 10 to the negative 11. So definitely we're going to have an acid here. Hopefully that makes a bit of sense. All right. Let's take a look at just a single hydrogen phosphate. And let's look at its pKa and pKb values. And let's see how about that one. What's this one going to react as? So its pKa and pKb we can figure out. Its pKa is going to be pKa 3, right? That's where we're removing our third proton from phosphoric acid. And so that will be a 12.37. If it's acting as a base, we know that if it's acting as a base, that's going to be the opposite process of pKa 2. So indeed it will be pKb 2. So we're going to be subtracting 14 minus pKa 2, which was 7.2. Which is 6.8. Awesome. And so as a result, we're going to see that this substance, the hydrogen phosphate, is more likely a base. It's more likely to react as a base, exactly. And in fact, yeah, this one would probably have a basic solution if you were to just put it in water, because its pKb is less than 7, for sure. Interestingly enough, we'll see that this one will also have a basic solution, interestingly enough, even though it's more likely to act as an acid. Just it's still going to be basic. Curious stuff, isn't it? Fun, fun, fun. So, the point of all this of a base compared to its conjugate acid or vice versa will dictate its behavior in solution. And so we have a couple of things we can kind of point out with this. So we're going to see that salts, which are made of conjugates, and spectator ions, can be various things. So we can tell a salt is going to be neutral if it is made of conjugates, of a strong acid plus a strong base. For example, sodium chloride would be a neutral one. Any sort of neutral salt of chloride would work. So we're going to see that this is going to be the conjugates of our strong bases, like sodium hydroxide is technically, sodium is not its conjugate, but that's a spectator ion. And so we're going to see that sodium will work there. We'll see that calcium chloride would also work, or calcium bromide, for example, or potassium iodide. All of these would be neutral, or potassium nitrate. All of these would be conjugates of strong acids and strong bases put together. So those salts would be neutral. Salts can be basic as well if it is a conjugate of a weak acid plus a strong base. So if it's the result of a reaction between a weak acid and a strong base, so something like sodium acetate. So acetate would be the conjugate of the weak acid acetic acid. Sodium fluoride would be another example. Potassium fluoride. What else do we have? What other nice weak acids do we have? Potassium cyanide would be another one. Where we have these conjugates that came from a weak acid. Those would be basic salts. So if you put sodium fluoride in solution, you're going to be expecting a high pH because that fluoride will be acting as a base, a weak base. All right, and the sodium will not do anything. You could also have acidic ones, which, guess what, are conjugates of strong acids and weak bases put together. So something like ammonium nitrate. We had the strong acid nitric acid, the weak base ammonia. Put those together, we make ammonium nitrate. That would be an example here. We're going to see also this category will include certain small, highly positive ions. For example, iron and aluminum are also actually pretty acidic. These will work in a little different manner, but these would also function as acidic salts. So if you had something like iron 3 nitrate would be an example of an acidic salt. We'll take a look at that in just a minute. Something like that, or even something like zinc chloride. Zinc is also going to be one of these, although it's not nearly as strong as iron or aluminum. These can still function as acids. And we're going to see what that looks like. So, but first let me just do our fourth category, and then we'll take a look at some of these metal ions. All right, let's look. Our last one is going to be the complicated one. So when you have complicated, so we had neutral, basic, acidic, and then complicated. This means that it's a conjugate of weak acids plus weak bases. So these ones you would have to look at both of them and calculate stuff. So for example, this would be something like ammonium fluoride or iron 3 acetate, where you have something that can act acidic and something that can act basic in the same salt. Or even, how about, what's another good one? I don't want to keep using ammonium as our kind of standard base here, but it's a good one. Whatever, this works. So with these, you would have to calculate or determine by looking at the at pKa's and pKb's. So if we look at ammonium fluoride, for example, we know that this could act as an acid and we would have a pKa for this, which I think we saw was, what, 9.25? We see that fluoride can act as a base. I'm just omitting the water if that's okay. Oops, sorry. The pKb is the pKa of HF. Oops, sorry, 14 minus that. So if you look up HF again, actually we have it here somewhere, don't we? Oops. Hydrofluoric acid, where did you go? 10. Oh, I guess we've already calculated it's, okay, we have 3.17 was its pKa. Which was 10.86. So looking at these two, what do we think? Who's gonna win here? So the ammonium is gonna win out over the fluoride ion here. And so we're going to see that this salt is most likely to create an acidic solution. And so now that I think about it, I think I've lied to you a little bit earlier. Yeah, I think I'm a liar. Let's go ahead and delete this because I think it's just a complete lie. This thingy. Let's get rid of this because this, now that I think about it, is just not true. That's not true. So that never happened. So we're going to see here that the ammonium fluoride is going to be acidic in solution unless we throw some other bases or stuff in there. So if we were to just dissolve ammonium fluoride, we're going to see that it's going to create an acidic solution because the pKa of the ammonium's reaction is going to be less than the pKb of the fluoride's reaction. And so let's go ahead and let's see if we can't ammonium fluoride. Let's see if we have any kind of fun stuff with this. Anything exciting here that we can see on its Wikipedia page? No, we have no constants given to us. But we're going to see that this is going to be a little bit acidic. So you can see the pK and pKb are pretty close here. And so it's going to be kind of a little bit acidic. It's not going to have a huge acidity, but the acid is going to win out here. All right. So complicated ones you have to look at both. But others you can kind of just eyeball looking at their formulas. All right, as a quick aside, let me talk about these metal ions here. Let's look at what happens when we introduce iron 3 into a water solution. We know that transition metals are going to be smaller than main group metals, right? So for example, like potassium, definitely iron is going to be smaller, right? We go further to the right on the periodic table. And we know that the more highly charged we are, the smaller we get as well. So iron 3 is a pretty small and pretty positive ion. And we're going to see that when this interacts with water, we're going to see that this ends up drawing more electron density, towards the oxygen. Because it's next to something so positive, and because it's so small it can get really close, that this will draw electron density toward oxygen, which weakens the OH bond. And if it's weaker, that means we're more likely to be able to pluck off that H+. So remember, the weaker your OH bond is going to be, the easier something is going to be able to pluck that hydrogen off. And so that's why we're going to see that these small positive ions are going to be able to form acidic solutions. We're going to see that these 3+ ions will generally have somewhere Ka's around 10 to the negative 5 or so. 10 to the negative 4, 10 to the negative 6, somewhere around there. 2+ ions will have Ka's of around 10 to the negative 10, 10 to the negative 11 or so. So definitely less strong compared to these 3+ ions. All right, so we can see that things like iron, aluminum, zinc, chromium, a lot of these ions can act quite acidically. And in fact, if we go ahead and, let's see, iron 3. Let's see if we can't find some, darn, Wikipedia doesn't have any value for this. Oh well, I tried. Oh wait, here we go. We have something about its thing, but I don't see a pKa value here. Oh well, somewhere around 10 to the negative 5 is what we're looking at here. So we're going to see that these ions will form potentially acidic salts. All right. Woohoo. Exciting. Are your minds blown yet? Maybe. Maybe not. All right, we're going to look. There's kind of 2 more things we'll look at. And then I think tomorrow we'll just do a lot of practice. So I want to get the kind of new content out of the way, and then tomorrow we'll practice it out. So we'll work with a bunch of these salts, and we'll kind of take a look at their acidity or basicity. So let's take a look at what are called Lewis acids and bases. So mostly we've been focusing on Bronsted-Lowry acids and bases where protons are moving around. The Lewis definition of acids and bases is going to be a bit broader, where a Lewis base will donate an electron pair, and a Lewis acid will accept an electron pair. So, for example, if we think about ammonia, it has a lone pair. And if we think about HCl, we're going to be having that ammonia kind of donate its lone pair to make ammonium chloride. We're going to be having that ammonia give its lone pair and bond with that hydrogen. And the chloride will come along because of the ionic attraction. But we can see here that the ammonia is going to be a base, and the HCl, of course, will be our acid. The ammonia is going to be using its electron pair to donate into that HCl. So this is more, again, about the chemistry. So instead of looking at where hydrogens are going, we're looking at what's happening with lone pairs. And so if we look at, for example, what's another good example here? We can look at this one. If we look at their Lewis structures, we could see what will happen here. Oh, sorry, little dude. Is we can have a lone pair attack this incomplete octet aluminum. As a result, we can make a complex between them. We're going to see that this will make some nasty complexes with charges that are not very friendly. And what you can actually end up having is some rearrangements happening where you actually kick off an HCl. And as a result, that HCl can go and react and split apart. And we can see here another means by which aluminum chloride would be acidic. So through this reaction with water, we're able to essentially produce a proton in solution by ripping it off of water. After water donated its lone pair to aluminum, aluminum is going to be acting as an acid. Oops. And our water is going to be acting as a base here. So these are a little bit tougher to kind of see with the lone pairs and all that involved. Suffice it to say, very similar things will happen with Bronsted-Lowry bases and acids here. So, I mean, technically, the proton is not being transferred to aluminum. It's being transferred to a chlorine instead. And we're going to be forming a new bond between aluminum and that hydroxide that's formed as a result. It's a bit strange, I understand. A bit less common. But suffice it to say, it's really a similar thing that's happening here. You just want to look at what's happening with lone pairs. Lewis acids we're going to see will will often be things that contain boron or aluminum or other group 13 elements, because they happen to have those very nice incomplete octets, right? They have 6 valence electrons in Lewis structures. Right? If we saw boron trihydride, it looks like that, right? We have an empty spot here that can accept a lone pair. It can accept a lone pair. And we're going to see that things in group 15 through 17 tend to be Lewis bases. So, for example, phosphine has that lone pair. Water has that lone pair. And of course, something like even the chloride ion has lone pairs that can give away. And so we can see that we can form complexes between these. We get to go into more like kind of complex chemistry here, but let's look at this one. We're going to form a complex between silver and ammonia. We're going to see, if we look at the Lewis structures of them, silver as a Lewis structure is completely empty. With ammonia, it's got a lone pair, right? We're going to see that this might look something like this, where overall we have a positive charge hanging around here, where those lone pairs are going to be used to complex with the metal. So metals are generally going to be your Lewis acids, like aluminum, like boron. Boron's a semi-metal, but close enough. And you can have other metal cations also acting as Lewis acids. Lewis bases, again, are going to be things with lone pairs, so those are going to be typically anions or things in group 15, 16, 17. Let's look at your homework for a second. I think there's a couple of examples we can do maybe from there. Let's see. Let's look at some of these Lewis acids and bases. All right, here's an example for you. All right, let's look at this. If we're to see what's acting as a Lewis acid or a Lewis base, this is an equilibrium reaction, but same idea. Let's draw the Lewis structures. If we're looking at this, these are a little bit easier to see. What's happening with the lone pairs here? So if we're looking at it as a Bronsted-Lowry, we can say, okay, a proton has moved off of H2O, and now it's on HCN. Water has lost a proton, therefore water is the acid. That's fair. But we can also explain that in terms of Lewis acid. So remember, a Lewis acid will accept a lone pair. And we can see that water has 2 lone pairs, and its conjugate has 3 lone pairs. So it has accepted a lone pair, therefore it's a Lewis acid. And we can see the reverse is going to be true. The cyanide ion has lost one of its lone pairs, instead. It has one fewer lone pair. How can I draw this? Whatever. 2 lone pairs. 1 lone pair. We can see the lone pair has shifted over. All right, same result as with the Bronsted-Lowry mechanism here, but it's broader because lone pairs are present in a lot more things than H's are. All right. So just like before, we're going to see water can act as a Lewis acid or a Lewis base, just like it can act as a Bronsted acid or a Bronsted base. So we're going to see we have a very similar pattern happening there. Have your minds exploded yet? Maybe. Let's take a look at one more. What the heck is happening here? Sulfur dioxide. Let's take a look at what's happening here. This is kind of a harder example. But let's see how this is gonna... Oh, I forgot some lone pairs. If we put these together, we have our sulfurous acid, right? Let's see. Are we going to have a lone pair on sulfur? Yes, we are. What's happened here? What has happened here? So we kind of have two options, right? One is our sulfur has given a lone pair to oxygen, or oxygen has given a lone pair to sulfur. And we're going to see that it's going to be the second case there. We're going to see that this lone pair is going to be essentially attacking that sulfur. Here, let's do it one step at a time. If we do this, this poor sulfur will be completely overloaded with electrons. And we're going to kind of form a complex there. And we're going to end up just having one of these oxygens is going to pluck away that hydrogen, just kind of like before. So with the HCl thing. And we're going to just kind of rearrange to form that guy. It's called a proton shift. We're going to do some rearrangement there because we're going to have a positive charge here and a negative charge on the sulfur. And so we're going to do some rearrangement there. Hi, little one. And so as a result, we're going to end up getting this. So we're going to see that our Lewis base is going to be the water, and our Lewis acid is going to be the sulfur. Notice we could not do it the other way around. Sulfur can go above 8 electrons, water cannot, oxygen cannot. So we can't give sulfur's electrons to oxygen. Not going to happen that way. Can't do it because we can't make oxygen have 10 electrons. All right, so that's going to be kind of another kind of hint you can use. So ones that can go into expanded octets can be Lewis acids, whereas the period 2 elements for oxygen and nitrogen and all that cannot be Lewis acids. At least in this sort of reaction. They can be Lewis acids in other situations. Isn't this terribly confusing? Well, let's pick this up tomorrow. I feel like we're not quite there yet on this particular topic. So we'll get there. Okay, so we'll get there tomorrow, and we'll take a look at what's happening. Okay? So we're out of time. We'll see you guys tomorrow. We'll continue this. We'll do a lot more practice with these salts, figuring out whether solutions are acidic or basic. Maybe we'll do some more ice table stuff. We'll have a good time. So I'll see you guys tomorrow. Enjoy the rest of your day. And we'll continue.